I like.
I got 0.5.
Shut up.
I got 0.5. Gives it this act perpendicular to the radius, which you can see that. That's what we were saying.
The correct answer is?
B.
Correct answer is B.
Okay.
So here is the net torque is equal to I alpha. Watch this. Remember to multiply by the radius. Okay? Maybe I shouldn't do that as a function. Just perpendicular radius. This right here is a really popular error for getting to multiply by the radius. So mr squared alpha so you have 0.5, sorry, nope, you have 1 times 0.5 divided by 1 kilogram times 1 meter squared, so 1, let's just have 0.5 for the radius. Okay. The reason I made this problem, making a distinction between R is, for a torque, is where the force is applied relative to the axis of rotation. In moment of inertia, it's where the mass is distributed. Okay, so please make a distinction between the two. Good with that? Have a conversation.
So much you. I think I was from the classroom. Those have to take the test now.
I guess look at how
That's true.
I guess this is the next day that has not changed.
Correct answer is
B.
B.
Bountiful buffalo.
That wasn't too bad, right?
What is this?
Yeah. So when you got something. Correct answer, or tell your neighbor. What do you think?
D. Okay, I think it's
Four. Oh. Now simply does. Over doubtful
over.
Solve this. So f1 times 0.5 is equal to 1 times 0.5 squared
Yeah.
acceleration. To get the acceleration, you have to angular acceleration. And then
What's the radius squared?
the radius is squared, yeah. But I just canceled out because they're multiplied on both sides, so that means 0.5. And the second one, sum of all forces is force 2 times 1. Because the radius is equal to 1 times 1 squared.
I'm confused, but I didn't, because I didn't do acceleration in the first one. It's just that one
That's a pretty fair answer.
over mr squared, which is 0.25, right? Because it's the radius. So that gives you 4 for your angular acceleration. The first one.
I'm not going crazy, right? That is
Correct answer is
D. For doubtful decimals.
D's for dog. Yeah, D's and E's.
Because I'm down with this math.
Yeah. 0.5 is going to cancel. I'm going to go with it. Yeah, I'm going to go for D as well.
Okay. So we have force times the radius is equal to mr squared.
Oh, wait.
Rotational. Turns out in both cases the R's are like capital R because they're forces acting on the rim for a specific wheel. So that knocks out one of those. So in order to have the same acceleration, they both have the same mass. That doesn't matter. Have half. This has half. Half of R, and this has R. And we're looking for that force. I like D.
Yeah.
For that.
Just solve for it.
Yeah. up when you go. Have a conversation.
What kind of energy, right? So what I'm trying to say is you have 1/2 I angular velocity squared. No, letter 3. I also can see. Yeah, it says bro.
Because you're trying.
I could use this so that they're gonna be which they might be.
So you got two.
Okay, so you know that both of them have like the energy right?
I got it.
But like,
Something happened.
oh wait, yeah, they don't have to be the same. But your normal kinetic energy is just going to be 1/2 mass, and then you sub the velocity for angular square. So it should be.
I interpreted my data.
I solved for velocity.
I also solve for velocity.
Oh, that would probably be a better idea.
Or you can't.
Yeah, angular times R, this guy. And then solve for angular velocity.
It doesn't have to be.
No, they plug in angular velocity.
Because they have to join.
I did. Oh, potential energy.
Like no, one can't go down any faster than the
The
other.
two kinetic energies.
I understand.
I'm trying to think really hard.
I understand how you're doing. Well, so you know that the kinetic energy is half, so that
No, I think I can.
Here's what I did. I mean,
He doesn't.
here's what I did.
Okay, what do you say?
C.
Answer is C. Good job.
Take it.
So,
Yeah.
okay, so that's of the descending ball. Okay. So the drum is going to have rotational kinetic energy 1/2 I omega squared. Okay. So 1/2 M R. Nope. 1/2 times 1/2 M R squared times speed squared over the radius squared because speed is equal to rotational speed times the radius. So that knocks that out. So you end up with 1/2 times so what you're trying to do is you're trying to get this expression out of this. So then you can go, oh, that's 1/2 times K. This K is equal to that. Good there? Okay. So when you're asked to compare and contrast something, what you're trying to do is rearrange the equation to factor, to be able to pull out this original thing, what you're comparing it to. Okay, so I had this expression, I need to modify it to get 1/2 mv squared. Be able to factor that out. Whatever's left, that's what coefficient you're multiplying by. Okay. That trick you'll use a lot. Okay. Good. All right. So, is mechanical energy conserved? This goes down.
Is there?
Yes.
Yeah, it looks like. Is there friction? Yes.
No friction.
Friction. Cool.
What about tension?
Oh.
Isn't that internal?
You like that?
Okay. So
I say wrong.
tension is a non-conservative force. It is doing work. If we looked at it as the ball by itself or as the drum by itself. Look at it as a system, it's inside, or you can say that the positive work done by tension on the drum is equal to negative work done by tension on the ball. Okay. Negate each other. Good with that?
So as a system, it's conserved, but individually, it's not.
Right. AP.
Thumbs up when you have a guess. Have a conversation.
The operator, because for the master ball, it also has to apply the torque on the disc. That's good.
But if you look at the little forward thing pulling it down, it's
The torque on the pulley. So tension pulls down. If we just
like if you
pull
look at the
straight
little circle
down,
what's it called?
the ball, what
The thing pulling it down.
well, it's accelerated, right? So if the tension was put to MGR, it wouldn't accelerate down.
Okay, yeah.
Back
I know,
up.
it's saying,
Yeah.
it's saying it's less than MGR. Because tension is
Isn't the whole point is at zero?
But if the
the wheel has nothing to do, so it will accelerate just with the force quicker, except for that.
yeah,
I think it's less than MGR. I think the tension is the thing.
Could be.
The tension is
One of
torque.
the-
I think the tension
I
is
just thought
torque.
kind of like.
I thought it's the
Correct answer is
A.
you got B's and A's. Find someone you disagree with. Prove to them that you're right and they're wrong.
Okay, so it has to be less than, right?
Why?
Because you know it's accelerating downwards. That means the tension has to be less than that, right? Or, wait. I might be wrong. Yeah, right?
So
If it's accelerating downwards, that means that you know that the sum of your forces are equal. Right? Wait, I need to write this out.
they're not equal. It's probably accelerated
It's gonna be
downwards.
tension minus.
Right, it's accelerated downwards, right?
It says
What's
it's accelerated downward.
Does it? No, it doesn't.
It says
I think
because of
we
gravity, the mass falls and the pole rotates.
That's pretty good. Yeah, I'll go with plus that.
Does it say this?
It doesn't say accelerated, it just says
Friction.
Oh,
has to be.
okay. Well then, If you know that, then you know that tension has to be greater.
Correct answer is
A. Oh, sorry, B. Yeah, it's still. I got the answer wrong again.
Yeah, I agree.
correct answer is B. Okay. If we looked at the free body diagram of the suspended mass, you have force of gravity, tension, you make the way it's moving positive. You have force of gravity minus tension is not equal to 0, but is equal to mass times acceleration, speeding up in the positive direction. Therefore, this has to be greater than that. And that same force of tension is being applied to the drum or pulley, so less. Okay. Here is a full-on example problem. So this is a Atwood machine or modified Atwood machine with a massive pulley. Okay. So what we're going to do is this. Do a free body diagram of the sled. So this is I'm just gonna say this is capital M rather than writing subscripts. It's annoying. Okay. So we got a force of tension. Okay. We got force of gravity. And normal force. Okay. Some of the forces in the x direction are not equal to 0. I'm going to make the way it's moving positive. So I've got force of tension is equal to mass times acceleration. Some of the forces in the y direction are equal to 0. Actually, start beating me. I'll give you like a minute head start. Start setting things up. Go. Start setting things. I want a free body diagram of the two masses, and then do the best you can with the pulley, just setting it up. Now you're just setting it up. I don't care what you're looking for. Now you're just setting things up. Oh, boogas. Oh, no. We're good. We're good. We're good. We're good. Okay. So, hopefully you got those two. Let's talk about the pulley. So, anytime something's going to rotate, you're going to want to draw an extended free body diagram. And so like where the forces are active on the object. So here we have force, tension, force, tension, gravity. I'm just going to put FG. And I'm going to go hardcore on this one so you can see the full on. Okay. So here, some of the forces in the X direction on the pulley, are they equal to 0? Why or why not? Some of the forces on the pulley. Tell your neighbor what you think and why you think it.
Must be accelerated.
Yeah, so even if you convert, like, because we know we're.
It's weird because the tension's over in different directions.
Okay, so ready?
The circles.
Here's how you know. You look at the motion of the center of mass. You do not look at the free body diagram. I mean, you can if you don't have any other clues, but you look at the motion. How is the motion of the center of mass of the pulley moving?
It's not.
It's not. It's staying at rest. So you know that the sum of the forces, both in the X and the Y, are both equal to 0. Is everybody okay with that statement? Okay, so we are missing a force, right? Because in the X direction, you've got this guy. There needs to be something that's being that cancels that out, that holds that pulley still. There's a force from the pivot that's doing something like that. We don't know what direction it is, but we do know it's going to the right somewhat. And, oh no, actually we do know, kind of. It has to counteract the downward forces of gravity and tension. It has to counteract the left force of tension. So it needs to be at some angle. We don't know the angle, but we know it's angled. Good? With that,
Where does that force come from?
the axle, the thing that's holding the pulley still. This thing. Okay? So, rarely do we need to deal with this, but it is a thing. Okay? That can be asked. Okay? So, you've got pivot in the X direction is like that component minus tension is equal to 0. And here you got the Y component of the pivot minus force of gravity minus tension is equal to 0. Okay. I'm just going to leave that there and say some of the torques. Are the sum of the torques equal to 0?
This one's
Tell your neighbor and tell them why you think.
spinning.
If you're some torques.
Yes.
So
But-
0.
No, the
No, it's parallel. The force is parallel. To the radius.
It has to have some
Perpendicular.
torque because it's spinning, because that object is
Correct answer is
No.
no. Why?
because it's spinning.
It's accelerated.
It's experiencing rotational acceleration. Is it possible for something to be spinning and have the net torque equal to 0?
Yes.
When?
It was already spinning.
If it's spinning at a constant rotational velocity. Constant angular velocity. And that torque can be equal to 0. Okay? You see the similarities between if something is moving, is it possible for some of the forces to be equal to 0? Yes, only if it's moving at a constant velocity. Okay? So, it's accelerating, so not equal to 0. So, what forces are exerting torque on the pulley? Is gravity. Is the pivot? No. That is why we often don't need to consider it. But they are there. And it can definitely surface. Okay? Specifically, what's the force of the pivot? Or the axle, sometimes they'll write. Okay? Then you just go to this. But if they don't ask for that, you don't need to do it. But it's there. It's definitely in the realm of possibilities. So we have force of tension times the radius because it's perpendicular. Are these going against each other or are they helping each other out?
Against each other.
They're going against each other, so we're subtracting this. And that's not equal to 0, so it's equal to I alpha. So the follow-up question is, are the forces of tension equal to each other? Oh, your neighbor, why or why not?
It can't be, because otherwise it'd be equal to 0.
They're supposed to.
Because if there's a
So if they're not equal, figure out which one's greater.
Oh gosh. Oh wait.
The
It's
one
more
going
and more
up.
forces. Yeah. Wait, yeah.
Yeah,
Easily.
because otherwise it would be spinning that way.
Well, turn down.
It has to. The tension going down has to be greater. Ready? Because we know
That
it's
makes sense.
accelerating.
Why is it not greater?
Correct answer is
One going down. So
one going down is greater. Okay? If this pulley was massless, then the tensions are equal. And oftentimes they will set up a problem like this that says you have a massless, frictionless pulley, or mass of the pulley is negligible, meaning it can be ignored. But if they don't say that, and they really like specify, hey, the pulley has a mass or has a moment of inertia, that's the thing. That must be reconciled. Okay? So this force, so we need to make a distinction between the two tensions. So this is FT1, 1, 1, 2, 2, 1, 2. Because the difference. You got to get something to make that pulley spin. This torque has to be greater than that torque to make it experience rotational acceleration. Okay? So now that's our setup. Okay? If you can do the setup, you can answer anything they throw at you in terms of acceleration, the coefficient of friction, anything like that. If they ask for something that looks like energy, well, then go the energy route. Okay? But this, you can hit forces and acceleration with this. Okay? If they ask for how fast, or how high, or how fast it's spinning, that kind of screams energy. Working energy. Okay? So here, we need to be able to tie the linear motion, or translational motion of the sled and the mass, and the rotational motion of the disk. And so we can say this is I acceleration over the radius. So this is tangential acceleration from this equation. Okay. And you got force of tension 2. Minus force of tension 1. Factor out the R. So you have force of tension 2 minus force of tension 1 is equal to I over R squared. Acceleration. And over here, I have an expression for FT1. And that's easy. MA. Expression for force of tension 2. That's mg minus ma. And that's a lowercase m. I've got mg minus ma equals I. All right, so bring everything with a to one side for solving for acceleration. Okay, so the only thing left is mg. So you get mg over, then factor out an a. I'm making a couple steps here. Let me know if I lost you in the dust. Okay with that? I got brought this MA over that MA over there all added because they're subtracted. I factored out the A and brought that, whatever is left, or like after I factored out the A over here. Okay. I'm going to teach you this. Don't use this. Don't write this on an exam. I'm just showing you this so that you can get to the answer quickly. Don't do this. Okay? Remember the snake? Like with a massless pulley? Okay? We can do the snake with this. The difference is, okay, so if we didn't have the massive pulley, the expression is like this would be the snake, right? This positive direction. Okay, what's acting on the head is just the force of gravity. There's nothing acting on the tail. And so we would say the net force is equal to mass times acceleration. So that's force of gravity is equal to the entire mass. So that's m plus m. And so the acceleration would be mg over m plus m. Yes? Okay. This is the stretch. This is the mass factor for the pulley. Okay. This is in kilograms. Kilograms plus kilograms plus kilograms. This is like how much inertia there is, how much inertia there is, how much inertia there is. Okay, that. Don't do that on a test. But you have that in your brain. So, like, here's what the answer should look like. Okay, does that make sense? Do not depend on shortcuts. They do a great job dismantling you if you just know shortcuts. Like, really? Why is this? And you're like, well, it's just because my teacher told me I can do that. Okay? Jump. Are you okay with me erasing this, getting rid of that? Tell your neighbor.
Did you have a problem with that? Yeah, it's so much more visually easy to see.
Correct answer is
C.
get a C. Do that. Have a conversation. Tell them why you think so.
Because the angle.
Well, it's because the force is a vector, and it's the vector of gravity comes downwards as your radius increases, and on the top of gravity, the angle decreases.
But yeah, it's less perpendicular.
Yeah.
Parallel.
Correct answer is B. Correct answer is B. Okay. Here's the extreme case. This is the maximum, it's perpendicular. The extreme case is here. How much torque is the force of gravity exerting? Zero. So it becomes less and less perpendicular to the radius vector. Here's your radius vector. Good with that?
Jeff, you just worked.
Same scenario. Correct answer is
B.
B. Okay, it just does the same thing as the torque. Right? Good with that? Same scenario. Thumbs up when you have a guess. Tell your neighbor.
Yeah, because it's not constant.
Well, yes, but you need gravity to be
Yeah, it's not constant.
Correct answer is?
B.
Correct answer is B. Can you use A?
No.
No. Why not?
The angular acceleration is not constant.
Acceleration is not constant. Kinematic equations fall apart. Acceleration changes. Make sure you know that. This is a calculus-based course.
Acceleration is going to change.
It's going to change.
Okay. All right.
Sure.
Real quick. Center of mass. The balancing point. If you have a multiple pieces, then what you can do is you can just pretend like, okay, that's the center of mass of that rectangle. This is the center of mass of that rod. And this is the center of mass of that triangle. And then consider that as point masses. And then you kind of like see where it balances. Like that's just conceptually, that's how you do the balance. Okay? If you are going to calculate the location of the center of mass, you're going to use this equation here. So it is a mass of one of the objects, like the point mass, you simplified down to point mass times the distance away from your origin, whatever you want your origin to be. Okay? So I'm going to pick this point here to be my square. And I'm going to make this my origin. Okay? So I'm going to say 0 meters times 2 kilograms plus, let's put this to be, that would be the center of mass of the road, yeah, nope, there, okay, and so that's 3 meters times 1 kilogram plus center of mass of that dude there. 1, 2, 3, 4, 5, 6, 7. 7 meters times 8 kilograms. All over. Now watch this. Here's where a popular error. You need to include the 2 kilograms, even though the radius is, or the distance is 0. So the total mass of the system. Okay. So 359 over 11, whatever that is. Okay, that's probably somewhere around here. So like it's less than 6. Like 1, 2, 3, 4, 5, 6, right there. That looks pretty good. Yeah. Okay. You can pick anywhere along here to be your origin. You can pick this point. You just need to make this a negative value of x. Okay. Good.